In this set of videos, we're going to be talking about operational amplifiers. And in this video specifically, we're going to be answering what is an operational amplifier and why should I care? We're going to approach that question with a few pictures and an analogy. There are a few pictures here that are particularly useful introductions to op-amps. In the lab, you're going to find that op-amps look like this. They're 8-pin integrated circuits. This middle picture shows how you'll draw op-amps on schematics. They're these triangular-shaped devices. Often you'll simplify them down to only having 3 terminals, the minus, plus, and output terminal. But don't forget that the power is really important. And finally, we're talking about op-amps because they're extremely important tools that are useful to general engineers. They solve a huge class of problems and they're pretty easy to use. You can think of them as tape for electronics. They're really good at sticking things together, especially if they weren't designed to fit. We'll unpack that metaphor over the next few slides. What does it mean to stick electrical things together? One way to interpret electrically sticking things together is allowing two systems to be connected without having them influencing each other. Op-amps are really good at that because they can explicitly fix loading problems. This slide depicts an equivalent circuit for an op-amp, which is a bit involved, and we'll explain the details of this model in later videos. But I'm including it here now to show off the fact that the voltage source driving V out doesn't have any series output impedance. That means that op-amps aren't loaded by anything. They can drive almost any impedance without noticing, at least at low current levels. And this model, which isn't exactly right but works for our purposes, also includes a resistor at the V plus and V minus inputs. That resistor is extremely large. It's often approximated as infinite, and that results in only about 5% error tops. So this means that op-amps also never load a circuit because they have extremely high input impedances. So that means you can put an op-amp between any two circuits to hide a large source impedance and drive a small load impedance. That behavior is called impedance buffering. The other way op-amps can be used to stick things together is that they can shift and scale voltages. The circuit shown here takes a small signal, amplifies it, and adds an offset to it. That small signal on the left would be really hard to measure, but the large one on the right is actually really easy to measure. It's also possible to add low-pass or high-pass filtering behavior into these shifting and scaling, which means you can help to filter out noise. This process of shifting, scaling, and filtering voltages is called signal conditioning, and op-amps are great for signal conditioning. You can configure them to do all kinds of different operations. And that's the second way that they help stick different electrical systems together. So in conclusion, op-amps solve a really wide class of problems. They're handy and easy to use. They have real applications. This is a part of the design work you do as a practicing electrical engineer. And the circuit design is easy. So they're a useful little piece of circuit design. They have two kind of major applications in E80. They're useful for buffering impedances because they have a very high input impedance and a very low output impedance. They can also be used for signal conditioning. You can create gains and offsets and filters out of op-amps. So over the course of this video set, we're going to talk about how to analyze op-amps. We're going to get some practice with that, and we're going to look at some common configurations that are going to be helpful to you.